So let's continue on with mass spec. If you remember yesterday, we finished by looking at a mass spec of pentane, and we said that there's a lot of information to be gained from a mass spec. The first and arguably most important piece of information is the molecular weight of your parent ion or your molecular ion, and that's the peak cluster furthest to the right, and the molecular ion is the tallest peak within that rightmost cluster. That tells you the mass of your molecule, assuming that there's a charge of 1, which 90% of the time it will be a charge of 1. And then we said that you get these clusters of peaks that are kind of sporadically placed throughout the rest of your spectrum, and those are your mass fragments that usually correspond to some sort of functional group getting chopped off, whether that's a methyl group, ethyl group, propyl group, or so on. And this is really useful, but let's talk about a couple useful tricks in mass spec, because right now we're only looking at hydrocarbons. There's one really useful trick that has to do with nitrogen. So let's take a look at pentane. What's the molecular weight of pentane again? Go up. Look at it. The molecular ion, that parent peak, is at 72. So we can write down, all right, this has a molecular weight of 72. And then if we look at something with an amine on it, this has a molecular weight of 73. So this is a really useful tool. What you notice is that hydrocarbons, or things containing oxygen and carbon and hydrogen, always have even numbers, but things that contain odd numbers of nitrogen also have an odd number. So odd numbers indicate that there is an odd number of nitrogens. So that can be a really useful tool. If you look at your parent ion or that molecular ion and it's odd, that screams that there's a nitrogen in there. However, let's look at this guy. Do you think this will be an even or an odd number? Even, because we've got 2 nitrogens. So it doesn't necessarily help that you have an even number. It doesn't say that you definitely don't have nitrogens, but it limits the possibilities a bit more. So this has a molecular weight of 74, and it's even because it has an even number of nitrogens. So that's a really useful trick. Next thing we're going to do is, if we go back up and we look at our peak for pentane, we said that the parent peak is really useful, but we also had this little peak over here. You guys see that? It's right next to that parent peak. It's one heavier. That's called our mass plus 1 peak. This is also very, very important and very, very useful. So let's take a look at our mass plus 1 peak. And we said that the mass plus 1 peak was due to what? Isotopes. Exactly. So the M plus 1 radical cation is due to heavy isotopes. So let's take a look at the most common isotopes that we see in organic chemistry. Obviously, since we're in organic chemistry, we deal with carbon. Carbon-12 is the most abundant isotope. So I'll make a table of abundance. Carbon-12 makes up 98.9% of all the carbon on our planet. If we go down to carbon-13, we have 1.1% of carbon-13. It's not a lot, but it's big enough to actually be seen in the mass spec. So if we had something like methane, we would expect our parent peak to show up at an intensity that's roughly 100 times bigger than that M plus 1 peak, right? But you can still see it. It's got a little tail there. Some people ask, well, why don't we see isotopes for other elements, and I wanted to show you guys why. Let's look at hydrogen. Protons, so H1, these are naturally abundant 99.96% of the time. If we look at deuterium, it's present in 0.1%. It's pretty negligible, it's tiny. Same thing with oxygen. If we look at O16 and O17, O16 is present in 99.96%, and oxygen's in oxygen 17 0.04%. So we see just one second in mass spec. However, these are negligible. Sorry, what was that question?
So hydrogen is 99.96. What about the rest of the 0.02?
Oh, that's a good question. What do you think could maybe be making up that difference? Yeah, tritium. Tritium's super rare. You run into exotic isotopes that are just not common. I mean, you can find them in weird places, like they've talked about mining tritium on the moon. If you've ever seen the movie Moon, they talk about that. But they're in really low abundance. Primarily when we're looking at hydrogen, we're looking at H1. When we're looking at oxygen, we're looking at O16. However, with carbon, we do have this fairly sizable amount of carbon-13. It's present 1.1% of the time. Does that make sense? So the question is, well, why do we care? This is really useful. This is useful for determining the number of carbons that we have. And in order to do this, we have to use some math. I'll show you guys the equation we use. The number of carbons we have in our sample can be found by taking our mass plus 1 intensity and we divide that by our molecular ion intensity. And we take this ratio and we multiply it by 100. So that basically tells us, all right, relatively what percentage of that pair is due to the M plus 1 peak. And then what we do is we divide that by the isotopic abundance of carbon-13, which is 1.1%. And this immediately gives us a strong clue as to the number of carbons we have in an unknown sample. So let's do an example of this, and you may want to bust out your calculators, unless you can do math on the fly, which I can't. Intense. So we've got our parent peak in this example at a mass to charge ratio of 68, and its relative intensity, I'm just throwing it out as an arbitrary 100%. And when we take our mass plus 1 peak, it's going to be at a mass to charge ratio of what? 69, we just add 1 to it. So don't look elsewhere in the spectrum. Look 1 heavier, not 2 or 3 or 4. And this one has a relative intensity of 4.3%. Question is, how many carbons do we have in the sample? Does anybody have an idea? 4. Yeah, we just plug it in, right? You do 4.3 divided by 100 times 100 divided by 1.1, and that's approximately 4 carbons in our sample. What do you think the rest of the mass is likely made up of?
Hydrogen.
Yeah, probably hydrogen, because if we try to add in a an oxygen, that's going to take up a huge mass. However, sometimes it does involve guessing and checking, so it may be a combination of oxygens and hydrogens. So we'll practice that here in a second. But let's do one more example. Let's say, again, we've got our parent peak at a mass to charge of 96 and a relative intensity of 19%, because normally our parent peak isn't our base peak, it's normally at a smaller percentage. And then our M+1 peak has a radical cation at a mass to charge of 97 with a relative intensity of 1.5. How many carbons do we have in this sample? Okay, so we do 1.5 divided by 19.0 times 100 divided by 1.1. That's approximately 7. Oftentimes people will say, well, what happens if it's a non-whole number? What if you get like 7.2? Do you round up?
No, you round down.
You round down. So normally we round down. This is an imperfect science, but it's a pretty good trick for simple organic molecules, as it gives you a rough idea of the number of carbons.
What about 7.8?
You still typically round down. I don't even know if I've ever seen a case where you round up. Does that make sense?
Regular rule for under 5 above.
Yeah, it doesn't follow normal rounding rules typically. It'd be pretty rare to see 7.8. I'd be a little bit worried that something else is going on in that. Let's take a look at this in terms of a real life example though. And this is one I pulled from the book. I really like the skill builder exercises from the book, but it says, use the relative abundance of the M+1 peak to propose a molecular formula for the following mass spec. And I have the data listed on the right along with the mass spectrum. So what I want you guys to do is to use this data to figure out how many carbons are in there. And then once you have the number of carbons, we need to figure out what the remaining atoms are that make up this molecule. Yep.
So is the relative height the intensity?
Yes. So we'll spend a minute working on this. You guys can talk with one another too. What do you think the first step is?
1.2 divided by 20.9.
Yeah, or we could say, let's first determine the mass of our molecule, right? It's 86. So that's an important piece of information. Next thing, after we find the mass of our molecule, is analyze that N+1 peak. So now the question is, how many carbons do we have in here?
5.
5. Okay, so we'll do 1.2. That's our mass plus 1 peak, divided by 20.9 times 100, divided by 1.1. That means we have probably 5 carbons.
We always use 1.1?
Yes, because that's the natural abundance of carbon-13, that heavier isotope. So we always use 1.1 when we're determining this.
Why do we use the mass when it's not in the formula?
What's that?
Why do we use the mass, the MZ, when we don't even use it in the formula? Why do we need it?
This MZ, that just tells you the weight of that fragment. It's a mass to charge ratio. So M is mass, Z is charge. Normally Z is 1, so this is just telling you the mass.
But why would we need it in order to solve this problem?
You need the relative intensities of these two peaks. That's really all that's important for determining the number of carbons. Yep.
In your first example, I think it came out to like 3.9.
It did.
So would we still round?
In that case, that's so close you'd probably round up, yeah.
3.8, 0.0, 3.9.
I don't know. So you'd have to sometimes use process of elimination and kind of go from there. That's what we're going to do next. So let's take a look at this. So we've got 5 carbons. We know that the molecular weight is 86. What's the mass of 5 carbons? Okay, so minus 5 times 12, that's 60. This is our mass of carbons, right? That leaves us with a mass of, what would that be, 26 left over? What do you think could account for that mass of 26? Could it be hydrogen?
I think so.
Could all of it be hydrogen? Could we have a molecule that's C5H26? Not without having Texas or even worse, Russian carbons with like 8 bonds. No, I'm sorry. I'm not making fun of Russians. I heard that called once because Russia's the biggest country. So we've got a leftover mass of 26. It can't all be hydrogen because we'd have like 8 bonds to some carbons. That's just not going to happen. So we use process of elimination. It doesn't sound elegant, but it's the way chemists use it. So let's just say, all right, let's say we've got 86 minus 5 times 12. That was our carbon set. So these account for our carbons. What was somebody else's idea? I thought I heard it back there. Yeah, minus an oxygen. So we do 1 times 16. We could say, well, maybe this is an oxygen. Why didn't you say nitrogen? Because it's an even number, right? If we look back up at our apparent mass, it's a mass of 86. It's not likely that we have 2 nitrogens, because that would be, what, a mass of 28, right? Which would mean we'd have no more hydrogens left. So it's not likely that we have 2 nitrogens in there. We probably have 1 oxygen. Okay? So that would leave us with a mass of what left over? 10? Okay, so 10 left over. What do you think this leftover mass is probably? Yeah, leftover hydrogen. Okay, so when we look at this, we can propose the molecular formula. And we could say, all right, this could be C5H10O as the molecular formula. We have to look at this and we have to come up with some ideas, but what I'll do is I'll show you guys some tricks for coming up with constitutional isomers that could maybe account for this. There's something called a hydrogen deficiency index, and we'll look at that later, but that tells you a little bit about your molecule, primarily how many pi bonds and how many rings you have in there.
What if we have an alkyl group there?
We could, right? This is a molecular formula.
Okay.
So let's just throw down an example here. So 1, 2, 3, 4, 1, 2, 3, 4, 5. It could be this, right? Or 1, 2, 3, 4, 5. It could be this. We really have no information regarding the functional group knowing what we know right now. We just know the molecular formula.
Yeah, we use the IR spectra to define the function.
We can use the IR, definitely. So that's a good question. If we're looking at these via IR, how could we tell if it's the one on the right?
The big
Yeah, we'd have the big tongue in that OH region around 3000. What about the one on the left? How could we tell if it's the one on the left? Yeah, big strong spike at around 1700 for our ketones. So you can use this in tandem with other forms of spectroscopy to narrow down your potential compound. All right, there's also another peak we've got to look at that occasionally shows up. This is called the M+2 peak. Trust me, the M+2 peak's easy. M+2 peak is an indication of bromine or chlorine. Br or Cl. And the reason behind this is if we look at chlorine, the most abundant isotope for chlorine is chlorine 35. This is abundant in 75.78% abundance. Chlorine 36 is actually quite rare, but the next most abundant isotope of chlorine is chlorine 37. So it's 2 mass units heavier. And this is abundant in a 24.22% abundance. Same thing with bromine. The most abundant form of bromine is bromine 79, and it's present 50.69% of the time. And then bromine doesn't really have bromine 80, but there is bromine 81 in a high abundance, and this is abundant 49.31% of the time.
Where is chlorine 36?
It exists, but it's so unabundant, I'm not even listing it. It's a tiny, tiny fraction. So if we look at these, let's take an example set of mass spectra. And let's look at the one on the bottom. Let me make this bigger if I can.
Is it 81 bromine or 82 bromine?
It's 81 bromine. Let's look at our mass spec though. Can you see the peaks in our parent set? Can you see how there's a peak, not 1 heavier, but 2 heavier that's quite large? That's our mass plus 2 peak. I know it's a little small, but you can see the mass plus 2, I'll highlight it in blue, is right here and right here.
So is the one in the middle mass plus 1?
Exactly. So you still have that mass plus 1 peak because we still have carbon in these, right, due to the benzene. However, we're observing mass plus 2 because we have chlorine or bromine. So anytime you see mass plus 2, you've narrowed it down to it having a bromine or a chlorine. Then the question is, well, how can we tell if it's a chlorine or if it's a bromine? The relative ratios, right? If we look at chlorine, this is roughly a 3-to-1 ratio. If we look down here, this mass plus 2 peak is roughly a third of the height of our parent peak, right? So this is also a 3-to-1 ratio. If we look at these two, these are approximately a 1-to-1 ratio. And if we look at our mass spec, give or take, this is also a 1-to-1 ratio. So pretty useful tool if you see the mass plus 2.
So if you had diagram of something, would it still be one peak showing up like this same spot?
Yeah, if you had 2 bromines, it would still be roughly 50-50. Yeah, normally you don't have multiple. I guess you could do a similar thing as what you do with the carbon, where you compare your M plus 2 to your parent ion and then divide it by 24.22 to determine the number of chlorines, but it's just not super common.
What's the highest one on the bromine?
That's a good question. So what do you guys think this parent peak is? If you notice, it's also present over here. Yeah, just the benzene ring. So if you pop off that bromine, that's your benzene fragment that came off. And why do you think it's showing up at a really high intensity? Yeah, it's very stable due to resonance. So resonance stabilizes cations. Stable cations exist a lot longer in the mass spec and show up at a high intensity.
But what about the left one?
What do you mean the left one?
This is not as high as the right one.
But remember, the key word on here is relative abundance. So I could have changed this scale so that all the peaks were tiny or all the peaks were large. It's just a relative abundance. So you're comparing peaks within the same spectrum. You don't typically compare one spectrum to another.
Okay. So we don't have some kind of absolute unit standard?
No. Chloe?
So there are 5 sections of lines in the second graph. Should there be one for each carbon? Or because that has the peak where the benzene ring is, it doesn't need to have one for each carbon to determine the number of carbons?
Yeah, it becomes a statistical game. So what's the probability of finding a benzene ring where every single carbon is carbon 13? It becomes so tiny that you really don't even see it on the mass spec. But you might have a probability of having 2 carbon 13s, but it gets really small. So it just becomes a statistics game at that point. What's the probability of having a certain combination of isotopes in your mass spec sample? Does that make sense?
Yeah. So if there is like a high resonance stabilization, then it's not going to matter anymore?
If there's a lot of resonance that stabilizes a cation, it just shows up at a higher intensity, and that's typically going to be your highest peak in terms of relative abundance. We'll see some examples of this.
So is chlorine 36 just isn't stable? Is that why there's not a lot of it?
Yeah, and I mean, that's kind of outside of the scope of this class, but if you remember back to general chemistry, there are some isotopes that are just naturally much, much more stable than others, and that has to do with nuclear forces. So, all right, so let's talk a little bit about mass fragments. And we've already alluded to mass fragments when we looked at pentane. We said that some carbocations show up more intensely. And we said that there's a higher probability of observing stable, and I'll put stable, oh, not stable, stable carbocation fragments. So typically primary carbocations don't show up at a very high relative abundance, but tertiary carbocations might. Same thing with allylic carbocations. Allylic carbocations are quite stable due to resonance, so they may show up super intensely. So let's take a look again at what stabilizes carbocations. First thing we went over in first term was hyperconjugation, where we said that tertiary carbocations are much more stable than secondary carbocations. Oops. And this is much more stable than a primary carbocation, and this is much more stable than a methyl carbocation. So typically, you can assign fragments based on the stability of a specific carbocation. The other thing that can stabilize them is resonance. Oops. And the first one we have is allylic. So let's take a look at an example. Let's say this is my molecular ion. So we started out with this compound. I slammed it with an electron beam and dislodged an electron from there. What do you think it will split into? Well, let's think about it this way. If we look at this, we could end up with a cation here. So imagine we're cleaving this bond. And so we've got a carbocation on that carbon where that bond used to be. And why do you think this cation is so stable? Well, we can delocalize those pi bonds around, right? So if we look at this, that positive charge can be delocalized across two carbons, and then we would end up with a methyl radical that popped off. Can we see the methyl radical on mass spec? Why not? There's no charge. However, this allyl radical or the allyl cation shows up very intensely because it's very stable. There's also a unique thing where you can see alcohols very intensely. Let's take a look at what's going on with alcohols. All right, let's imagine this alcohol. And imagine that I'm bombarding this molecule with a beam of electrons. What electrons do you think will be most easily dislodged? Yeah, the lone pairs on the oxygen, right? If we think about a lone pair, it's just sticking out into empty space, more or less. The lone pairs are very exposed. So when we do this, we would end up knocking out one of those electrons, meaning we've got an unfulfilled lone pair. We have a single electron on that oxygen. And therefore, this is now a cation. Okay? And then what I'm going to do is I'm going to label my carbons. So what will this carbon be labeled, that red one? Should I label it alpha, beta, gamma? Alpha. So I'll go over here and then I'll say, all right, this carbon right here is beta because it's one away from where that alcohol attached. And what ends up happening is you end up with an alpha-beta cleavage. So let's draw our arrows. This single electron will hop down. It will steal an electron from this alpha-beta bond. So remember, anytime you're moving single electrons, you do single-headed arrows. And then what do you think we're missing? Yeah, we've got one electron left, so we'll just move that over to the adjacent beta carbon.
So you're breaking that.
Yeah, exactly. So we're going to cut up that alpha-beta bond. And let's look at our resulting product. So we have an oxygen-carbon double bond. This oxygen has a lone pair on it. Do we have any formal charges? Plus where? On the oxygen. Okay. And why do you think this fragment is super stable? Resonance, right? So if we look at this, we can draw a resonance structure where we can move this pi bond up to the oxygen. And if we do that, we now move that positive charge over to that carbon. And then last but not least, we end up with this ethyl radical. So I'll draw in that ethyl radical over here. So this is stabilized.
So the double bond just went to the oxygen, like those electrons?
Exactly. So let me even draw in the lone pairs just so we're keeping track of all our electrons. So this is very stable due to resonance. Yep.
Can we break the bond between the other beta?
Yeah, definitely. Any alpha-beta bond on an alcohol can be cleaved in this fashion. I just picked one of
That
them.
doesn't matter.
Yeah, you could pick either one.
Going back to the previous example with the breaking the pi bond
Mhm.
or carbon chain, since the pi bond is in a p orbital and then the electrons stick up and down, does that make it more likely for the electron to be kicked off versus one that's a single bond? Or?
That's a little tricky question. It's not as likely as a lone pair, for example. A lone pair is just sticking out into naked space. Those are really easy to dislodge. Breaking a pi bond, they are weaker than sigma bonds, so I would guess that you could do that if that's an available option. We'll see some examples. It makes a lot more sense when you're analyzing mass fragments just to cut up individual bonds, and then if you see an alcohol, remember, hey, we can cut this alpha-beta bond and get a really stable fragment out of that. So let's take a look at another one. Let's take a look at an amine. And I'll pick the analogous amine here. So we've got N. So imagine we have this amine and we bombard it with electrons. What electrons will get dislodged? Lone pair. So I'll just really bold this and I'll show this nitrogen as having a positive charge. So this is our parent ion. And then again, we want to go through and label our alpha and our beta position. And let's try to anticipate how this cleaves. Well, it's probably going to look a lot like the alcohol. So we'll cleave this alpha-beta bond and take one electron over to that beta carbon. Now when we do this, this nitrogen has a positive charge. So we formed an aminium ion, and this can be resonance stabilized, where we can move this pi bond up to this nitrogen and delocalize that positive charge across the carbon. And then just like before, we also have this ethyl radical that is invisible by mass spec, but the cleavage of amines and alcohols typically gives a very strong fragment that's the result of alpha-beta cleavage.
You just forget to put the other nitrogen.
What did I do? Oh, yes, thank you. Good catch. All right. There's a lot of clues we can look at. And so let's make a list of clues. These become like a giant puzzle. The more clues you have, the easier it is to solve. Let's say we have a mass minus 15 peak, meaning we see our parent or molecular ion, but we see another fragment that's 15 mass units lighter. What do you think this probably corresponds to? Yeah, loss of a methyl. So if we pop off a methyl group that weighs 15, we saw this with pentane, right? Where we had mass fragments where we lopped off individual carbons. What about mass minus 29? It's another CH2 added on, so that's probably loss of ethyl. We could do mass minus 43. This is loss of propyl. And in this case, are we losing a methyl, ethyl, or propyl cation? No, it's a radical. The peak that we're observing is the cation. And we can keep on going down. I'll just stop at butyl. However, there's a couple other really useful ones as well. So I'll show you guys the others that are unique. M minus 18. What commonly has a molecular weight of 18? Water. So loss of water. The question is, how can we lose water? And I'll give you guys a hint. It's from an alcohol. And the other one is going to be mass minus X. And I'm going to put a little asterisk there. And this is something called the Mclafferty rearrangement. And this is indicative of a ketone or an aldehyde.
So last two is not radical?
No, it's still a radical. Or actually, I take that back. It's mass minus 18 is loss of neutral water. With the Mclafferty rearrangement, you're not losing a radical, you're losing a neutral fragment as well. Let me make a little asterisk for this X down here. X is going to be an even number. So if we have mass minus some even number, there's a chance that we went through some sort of Mclafferty rearrangement. All right, so let's take a look at how we can lose water. And let's take our alcohol again. I'll do 2-butanol. And imagine we're bombarding this with electrons. We're going to dislodge one of these lone pairs, so I'll draw a single electron down there. That means this oxygen has a positive charge because one of its lone pair electrons is gone. Let's label our carbons. So I've got alpha, beta, then over here I'll put gamma. It's kind of dangling off in the distance. What? Yep.
It will never go to the other beta, right?
In this case, it could occur on either side. I'm just choosing these 3 carbons to focus on.
Is there one that favors one?
Not necessarily. It depends on your resulting cation fragment. Yeah, quite often you'll see both though. So let's take a look at this. In our gamma position, we've got some protons, right? So I'll just draw in our gamma protons. What ends up happening is that this oxygen radical will abstract a gamma proton.
Why?
I don't know. But let's take a look at the resulting product. This is what was found from experimental evidence in the 1950s. So I'm not sure why gamma is preferred over positions further away in the chain, but the experimental evidence shows that it is the gamma proton that gets abstracted. So let's do our arrow pushing. When we do this, we get H2O. That's our loss of our neutral water molecule. And then if we look at our remaining positions, I'll draw in these two remaining hydrogens. We've got our alpha position here, or our former alpha position, our beta position there, our gamma position there. What should be at the alpha position now? A positive charge, right? Because it lost that sigma bond that used to be attached there. We moved both electrons. And then what about the gamma position? Yeah, just a radical. It got one electron. So this will be this can be observed by mass spec. So anytime you see mass minus 18, that's a good clue that you've lost water somehow and that you maybe had an alcohol as your unknown starting material. So let me even put down alcohols. You don't really see this with amines. You typically only see this with alcohols. All right, let's do the Mclafferty rearrangement.
Wait.
Yep.
What if you didn't have a gamma carbon?
What if you don't have a gamma carbon? Then you might not observe that minus 18 peak very well. But you could still observe alpha beta cleavage. Okay, so the Mclafferty rearrangement. Let's say we've got this ketone, and I'm just going to call this an R group. Again, if we do this, we could have one of these lone pairs get dislodged by an electron beam, so that oxygen becomes a cation. What I'm going to do is I'm going to rearrange this to draw it into a different fashion. And with aldehydes and ketones, we go alpha, beta, gamma. So we don't start alpha at the carbonyl carbon. And let's redraw this so that it looks more like this. So I've got alpha, beta, gamma. And so you can see all I've done is twisted the tail around. And then just like with the loss of water, we have protons coming off of this gamma position. So I'll just draw one of those in. And just like with water, this oxygen can abstract a gamma proton. And in this case, what ends up happening is one of these electrons will actually go down here, and then we'll also observe alpha beta cleavage. And then the last electron goes onto the alpha position. Pretty crazy. So you've got movement of 5 total electrons in this rearrangement reaction. And so when you think about what happens, the bond between beta and gamma forms what? A double bond, right? So let's put beta here and gamma down here. This is our even molecular weight lost piece, right? So I said with the Mclafferty rearrangement, you always lose an even piece because you're losing something that has a double bond in it, right? And occasionally you'll see it where it's not dead on even, but it's a good indication. Then let's draw our other fragment, that's our cationic fragment. we've got this radical over here. And why is this so stable? Yeah, through resonance. So let's draw the resonance structure. So we can move this here, and move one of these electrons up. Oops, let me clean this up. And now the positive charge is delocalized across that oxygen. All right, so now let's take a look at common fragments. So common fragments for the Mclafferty. So what if that R is a methyl group? What will this fragment weigh? Does anybody have an idea? Not everybody all at once. We've got 3 carbons. We've got, how many would that be? 6 hydrogens and 1 oxygen?
55.
Is it 55? All right. Time to bust out the calculator. 3 times 12 for our 3 carbons, plus 6 hydrogens, plus 16 equals 58. All right, so if R equals CH3, we've got a fragment that shows up at around 58. So that can be a good clue. What about if R equals ethyl? What do you guys think? $72. So if we've got an ethyl group coming off that R position, we might see a peak at 72. What about if this is an aldehyde? This is a useful fragment. What do you guys think? 44, right? Please tell me my math was right there. We've got 2 carbons. We've got, what would that be? 1, 2, 3, 4 hydrogens, 1 oxygen. So that should be 44. So if you see any of these peaks, it's a good indication that either you had some sort of methyl ketone originally, an ethyl ketone, or an aldehyde. So these can be really valuable clues. What we'll do next week in lab is, instead of doing a wet chemistry lab, I'm actually just going to give you sets of problems, and you guys get to rack your brain on that for the entire lab period and work in small groups, and then it will be due the following lab period. So next week we'll finish up really quickly with mass spec, and then we'll jump straight into NMR.